Hello everyone, welcome to this presentation. My name is Li Sicheng. We also have Xu Di, Lou Jian, Wang Fu, and YK as the co-author from Alibaba Group, Alibaba Cloud, Alibaba Damo Academy, and T-Hat. First of all, I would like to thank OCP to host this event, virtual event and have us to present our work towards AI-assist video compression. The goal of this work is to bridge the divergence of traditional video codec design and computational intelligence. We will present a set of innovations in algorithm optimization, hardware implementation, and the interactive design process across these two domains. We will also identify design challenges and opportunities to provide the OCP community with some groundwork and the potential directions for future research. Due to the rapid growth of video applications and the boosting demand for higher video quality, the volume of video data increased explosive worldwide. On that occasion, millions of video will be delivered through the internet every second. Besides, to enhance realistic and immersive video quality, as shown in this figure, the spatial resolution of video grows continuously to enhance video clarity, and the spectrum develops from color with RGB to HDR, and the video frame rate could increase to 120 frames per second or even higher. Significantly large data volume is required to represent high fidelity and details in future video content. Video compression refers to the computing technologies that remove spatial, temporal, visual, and statistical redundancy in the original signals so as to facilitate data transmission, storage, and computing. In the past 3 decades, a series of video coding standard has been published, including AVC, HEVC, and open source VP9 and AV1, so on and so on. Well, these standards have been well engineered and thoroughly tuned on both hardware and software. The fundamental of the existing video coding scheme have not been changed thoroughly, as shown in this figure, although the bandwidth requirement of the latest AV1 is 8 times less than the compression with the MPEG2. The design complexity in terms of hardware cost, memory access, and computing power increased dramatically to 125 plus more, achieving high coding efficiency and to close the design complexity gap with novel mechanism become an urgent mission for video compression optimizations. And at the same time, many emerging works have applied AI or machine learning to the field of video compression and surpass the commercial video codec by significantly margins. However, this technology is far from saturating to its full potential and calls for comprehensive research and development effort in both academia and industry communities. At Alibaba, we propose the AI-assisted video compression for coding efficiency enhancement and also enables intelligent video processing. Firstly, we integrate the AI engine with a traditional video codec in a tightly coupled manner to enhance video compression. For example, refined variable block size partitioning, which reduce coding residuals and improve prediction accuracy. However, the optimal partitioning incurs high computational complexity to perform an exhaustive search. Formulating this mode decision process to fit a binary classification problem is a feasible heuristic solution, which could be well solved by traditional machine learning techniques such as support vector machine, decision tree, and so on. In addition, such an architecture is capable of merging recognition tasks with video coding tasks. For example, we will later demonstrate this idea on an ROI-based video encoding, which is ROI. ROI means region of interest based encoding. Uh, Secondly, we propose a fused architecture to jointly optimize for video compression. As shown in this figure C, based on this architecture, two research directions are identified. First, hybrid schemes that contain AI-based building blocks within traditional codec. And second, an end-to-end coding solution that are built primarily upon AI or deep learning. And in this figure D, we illustrate a deep learning based intra-prediction module to remove the spatial redundancy and generate flexible prediction patterns. Such a hybrid prediction solution has demonstrated the compression efficiency beyond HEVC, which is the most widely used compression techniques. However, remains largely unexplored on the trade-off between compression ratio, coding complexity, and the semantic quality. Here, we use an ROI enhanced video encoding application as an example to demonstrate our AI assist video codec and its hardware implementation on FPGA. Um, as you may know, ROI stands for the region of interest. The idea is very simple, saying when we have an image, the ROI region is the region that we pay attention to, and we usually give high bit rate or high, therefore they gonna have a better visual quality. And the background we usually ignore it, so we give it a little bit low bit rate. In this scheme, the bit rate saving at the same visual quality could be 50% to 25% compression ratio improvement, or giving the same bit rate, we can see a clear visual quality in terms of PSNR improvement. However, when we have a video codec, they can even though they can do uh, ROI coding, but we also need AI or a deep learning module to recognize the region, the ROI region for the codec. So based on this idea, we use FPGA from Xilinx, which they have a video codec unit called VCU on the FPGA, and also have reconfigurable logic that we can use to implement an AI engine and other control logic. So in this figure, we will show a demo saying when I get my some picture from a laptop and then send it to the FPGA board, and then FPGA board do the ROI enhanced video coding and then send it to another monitor to display. Okay, so this is the demo. We use HEVC as a basic coding scheme, and we use 1080p as the resolution, and we set the bit rate at the 50K bit per second. And the AI engine will recognize my face and then send it to the video codec for video coding. As you can see, my face is very clear, but the background is very blurred, cannot recognize very clearly as my face. And in this small window, we will see we can achieve frame per second as of 30. And here is the implementation result, saying my computer or my laptop is the video source, and then send it to FPGA board and then showing on another monitor. Here we want to summarize the benefit from AI assist video codec on hardware. First, it is going to enable a lot of intelligent video analytics First, we show its usage on improve uh, visual quality, and we also can apply AI-assisted video codec on surveillance applications to recognize human beings or other objects. We can also apply this idea on video conferencing to recognize sounds or speech during the video conferencing using an RNN model to implement as a natural language processing unit. Also, we can filter or flag inappropriate contents using this idea or use this idea in computational storage. Also, AI-assisted video codec on hardware can reduce latency overhead on a lot of live streaming applications. As you can see from this figure, it shows a traditional solution for video surveillance. Usually, we need to use a CPU to do encoding, decoding with a bit stream, and then do some image processing, and then send it the original image through PCIe to a GPU unit to do some machine learning applications like object detection or tracking, and then send it the result through PCIe again to CPU to do video encoding or other advanced analytics tasks. However, when we have an all-in-one silicon solution, we can do all this functionality together in an SoC, and so as to we can see 75% latency reduction with this all-in-one solution. As a conclusion, in this work, we propose a software-hardware co-design framework to facilitate the design trade-off between video compression ratio, the computational cost, and design flexibility. And we think OCP is a great platform for us to look for partners who are interested in this concept, and we would like to build the hardware accelerator together. The accelerator could be in form of an FPGA or an ASIC. Even though all parties who participate in this project may have these diverse video applications, we believe that they can all benefit from this hardware accelerator while being differentiated by their own software stack. Thank you. Thank you for coming to this presentation.